So let's look at another example of a of an operator. In this case, let's use the material implication. So as you know, the material implication has a slot on one side, which we can represent again with a square, and it has a slot on the other side. These two slots need to be filled with expressions that are well-formed formulas, but it doesn't matter what degree of complexity they are. The simplest instantiation of this would be to use atomic expressions like P implies Q. And of course, if we do that, we get a basic proposition, P implies Q, which it should be obvious by now is a well-formed formula because it satisfies both the pattern, P, a well-formed formula, is in the square slot, Q, a well-formed formula, is in the triangular slot, right? And it also because the two slots are the two slots that belong to material implication, it generates a well-formed formula. But as we saw in the previous example, we can put expressions of considerably more complexity together to create molecular propositions that still maintain this basic form. So these expressions are the same logical form. So over here, for instance, we might write P and Q, and on this side we might write T or S. Okay, so let's just say we had these two expressions filling the square slot and the triangular slot of this material implication. How would we write that? We would have to indicate that P and Q serve the function of the square slot by grouping them together or indicating that they function as a single unit. In other words, they fill a single slot. And then over here, we'd have to use groupers to indicate that T or S serves the same function. It's a single unit that fills the triangular slot. And then we connect these together with the material implication. And one more time, let me just say explicitly, this expression is a well-formed formula that follows this logical form. In other words, it's a material implication. And the only difference between this simpler expression and this more complex expression is that the slots are filled with more complex, well-formed formulas in the latter case than in the former case. Here, just to take one example, the atomic expression P fills the square slot, but here P and Q fills that square slot. Over here, Q fills the triangular slot to generate this expression, and in this case, T or S fills the triangular slot to generate this expression. Now, one thing I want to point out, it may seem obvious to you, but I just want to say this explicitly. This expression, P implies Q, is a completely different expression than P and Q implies T or S. In other words, the P and the Q that are involved are variables, so they stand for any proposition that, as long as it is a proposition with a truth value. And so for that reason, we can reuse this variable to stand in for some unknown proposition simply because the variable contains the whole range of truth values. It could be true or it could be false. All right, that's a beginning. Now let's consider operator scope. In this part of our discussion, let's start with some expression that's a molecular expression like P and Q is equivalent to R or S. All right? So you should be familiar with all of these symbols. We have some variables. We have the operator and, we have the operator or, and we have material equivalence here in the middle. Okay, fine. Now, here is a question about the operator that has the largest scope. How would we determine that? Well, the simplest way to do it is to think about where the slots are. So, for instance, What are the slots for this and? Well, on one side, it's P, and on the other side, it's Q, right? What are the slots for this or? Well, on this side, it's R, and on this side, it's S. So notice this sort of familiar pattern. You have a slot on the left-hand side, you have a slot on the right-hand side for binary operators, and they have to be filled with something, right? Now, what is in the left-hand slot, which we're using square to represent that left-hand slot, of this material equivalence? Well, it's this whole expression. So there's the square. It's really a rectangle. What is in the right-hand slot? That is what we're calling the triangle, and that expression is R or S. So the first question that one would ask about scope when we're trying to ascertain the proper scope order for operators is, which is the operator of largest scope? In other words, which is the operator that has the biggest expressions in its slot or slots? So have a look at it from this perspective. This seems really simplistic, but if your point of reference is the material equivalence, the slot on the left, the square, has a lot in it, and the slot on the right has a lot in it. But if you shift your point of reference to this and, then the two slots for that and, the square on the left and the triangle on the right, have a lot smaller expression in it, and it's a constituent part of this much larger expression. So if you think about it from that perspective, in other words, which operator operates on the biggest slots, then whichever operator is the operator that operates on the biggest slots is called the major operator. So in this expression, in this whole expression, the material equivalence is the major operator. And the major operator is going to be the operator of largest scope.